My name is Astrid Mueller. I'm an assistant professor at the Department of Chemical Engineering at the University of Rochester. I started here in August 2018, and I came from Caltech, where I was a staff scientist. This is my group here at Rochester. Here on the left, outside pre-COVID at the Genesee River, that is just at a park that's right on campus. And down here on the right, in COVID times, of course, where everyone is in their own room or has a mask on. But importantly, we develop nanocatalysts for clean energy solutions. Why do we need those? Of course, current energy use means CO2 emissions, and that changes our climate. The solution for this is to harness the sun's energy, because more global solar power strikes Earth in only 1.5 hours than we as humanity use in an entire year. What's also needed is energy storage and transportation. So we need to develop solar fuels with the aim that future energy use means no net CO2 emissions. And of course, the global availability of clean energy is a great socioeconomic equalizer. And this is exactly what we do. So how can we get this? We can have two different device designs. One is mimicked after nature, it's called artificial photosynthesis. And the other one is just electrocatalysis with solar electricity as energy input. But in any case, we need catalysts. And they need to be robust, efficient, selective, non-precious, and non-toxic. And that means that we need precisely controlled, complex, inorganic nanomaterials. And that is exactly what we do. We develop catalysts for solar fuels. And we do this, we accelerate the discovery of these high-performance catalysts by rational design. We use a synthesis method of these catalysts that is laser-based and allows us to make precisely controlled nanostructures, which we then characterize very well physically. We also assess the catalytic performance, and we elucidate the mechanisms, because once we know how they work, we can make better catalysts. Here's how the laser synthesis method works. A pulse laser hits a solid that's immersed in a liquid. A plasma is confined by this liquid that is formed after the laser hits with very high temperatures and pressures. That creates the formation of a shock wave, which rips this plasma very rapidly apart, and nanoparticles are generated upon this rapid expansion and cooling of matter. There are several advantages of the method. We can independently control properties such as size, composition, crystal phase, defect, densities, and so on. We can easily make metastable materials and mixed metal materials. No surfactants are necessary, and the synthesis is rapid. And it's rapid enough to make these 14 materials down here in 2 days. We use this method to develop water oxidation catalysts. And water oxidation is, of course, the liberation of oxygen from water. And it is needed to liberate the protons and electron or oxidizing equivalents to make everything from our most abundant feedstocks with solar energy as input that we really need, which is fuels, commodity chemicals, pharmaceuticals, and fertilizers. We also work on the other side of the device, which is CO2 reduction. This is a hugely popular field. There were almost 8,000 publications in the year 2019. And it takes CO2 through this electrocatalysis process and makes liquid fuels out of it that when we burn them, emit CO2 again. So the process is carbon neutral by recycling and contributes to decarbonization of our energy landscape. Here's what we are after. We are after these very precisely controlled catalyst surfaces in nanocatalysts, where we take CO2 and protons and electrons. And then with high activity, high selectivity, and high stability, make single products, be it liquid fuels such as ethanol and isopropanol, or upgraded chemicals such as the polymer precursors ethylene. Here's how it is to work in my lab. These are my students, of course, fully equipped: electrochemistry, gas chromatography. We have a laser system to make these materials, water purification, and so on. And you see they're all happy. We are also having our own SEM with EDAX system to have elemental analysis of all materials that we make. We are a diverse group working in truly interdisciplinary research. We work at the nexus of chemical engineering, chemistry, materials science, catalysis, surface and interfaces, and laser physics to make clean energy a reality. If you have questions or want more information, here's my group's webpage, and I hope to see you soon.